Okay, so last time we started looking into the fourth type of AC power. It's called complex power, right? And um, we learned that complex power consists of two types of power, right? P and Q right here. So you have uh, P and Q. So complex power is equal to P plus JQ, and from this equation we can observe that again complex power has the two different types, average power P and reactive Q, right? And this is also the reason why we call this complex power, because as you can see, P is the real part of the complex power, and Q turns out to be the not reactive, the imaginary part of the complex power, right? And complex power is a complex number, right? And again, that's why we call this complex number. In terms of the equation, that's one of them, right? But initially, the equation of complex power is defined to be um, the product of the voltage and the current complex conjugate, right? So voltage times current complex conjugate, right? If you use RMS, then there is no 1/2. That's the example of it, right? If you use RMS. If you are using peak values, then the 1/2 should be there. Don't forget the 1/2 if you use peak values, right? So you have the first equation for complex power, the second equation, and the third one right here, right? Okay. Any questions so far? And we talked about this example, right? We went over this example last time. So then now this right here, the fact that complex power is a complex number, right? Therefore, we know that for a complex number, we should be able to convert it into a polar form, right? Um, so this complex number right here, I could convert it into a polar form that has the magnitude of the complex power and the angle of that complex power, right? Again, if you convert that into polar form. Agree? Yes? So then uh, this brings us to the last type of AC power, right? We have four so far, right? We have instantaneous power, we have average power, we have reactive power, and then now we have complex power. The very last type relates to complex power. Specifically, is actually the magnitude of the complex power. So this right here, this portion right here, the magnitude of the complex power gives us the last type of AC power called apparent power. So that's what I have next, right here, is apparent power. Right. The symbol of apparent power is just like I showed you earlier. That's the magnitude of complex power, and the unit of it is volt amps, just like the complex power. So the unit of complex power is the same as the unit for apparent power. They are both volt amps. Right. And the equation for apparent power, there are several equations, but we also know from the previous equation right here. What is it? Right there, right? Let's start from here. And let me use a different page right here. So start from complex, complex power. Complex power is equal to P plus JQ, right? And what we need to look for is the magnitude of this, right? The magnitude of complex power, right? Now, previously we learned about P and Q, right? Anybody remembers what the equation for P and Q is in terms of RMS? Is V RMS, I RMS, and then what? Anybody? Come on. VI times, if I use peak, maybe you remember the peak equations. 1/2 VM IM, and then what?
Someone in chat said cosine theta v minus theta I.
That's correct, yes. Yeah, sorry, I'm not checking the chat right now. Cosine theta v minus theta I. Very good. Right. And then if I want to use RMS, then it's going to be V RMS times I RMS cosine of theta v minus theta I. And I'm just going to replace theta v minus theta I to be equal to theta, just to make it shorter, right? So therefore, P is equal to V RMS, I RMS cosine of theta. What about Q? Can anybody tell me what Q is?
It's of the same form, but instead of cosine, we use sine.
Very good. V RMS, I RMS, sine of. I'm going to make it shorter, so theta, right? Keep in mind that theta is again is theta v minus theta I. So now we have the two equations, right, for P and for Q. And now we're looking for the magnitude of this, right? And we learned that the magnitude of a real number, a complex number, is equal to square root of the real part square plus the imaginary part square, right? And so I can plug in the equation for P there and the equation for Q there, right? So then I get what? I get square root of VI, right, cosine of theta square plus VI sine of theta square, right? The whole thing under the square root, right? And by doing this, I can see that I can actually take out or factor out VI from the square root, right? And you get, well, that's too long. And you get square root of cosine square of theta plus sine square of theta, right? Just like this. And you know what this is, right? Under the square root, what is it equal to?
1.
1, right? So therefore, now we know that another equation for apparent power is actually V times I, right? V times I, right? So that's the equation I have right here. Let me put it here first. So that's the equation that I just derived, is that from the fact that complex power is equal to P plus JQ, I can then find the magnitude using square root of P squared plus Q squared, knowing that P is VI cosine, Q is VI sine, and you just plug those in to the equations, then you get the equation for power, for apparent power to be equal to V times I, right? Any question on this derivation? So that's what I have right here, that the equation for S is equal to VRMS times IRMS. If I want to use peak values, then of course it's going to be equal to 1/2 V peak times I peak. Okay. Any questions? Again, I rewrite the average power equation. That's 1/2 VM IM cosine of theta V in terms of peak values, and VRMS IRMS cosine of theta V minus theta I in terms of RMS. Notice that a portion of the equation for P, a portion of it right here, is VRMS times IRMS. Isn't that our apparent power right there? So now we have another equation for P. So right here, right? So P is equal to V RMS I RMS times cosine of theta V minus theta I. But then VRMS times IRMS by itself, right there, right, is equal to S, apparent power. So now we have, again, another equation for average power, which is equal to apparent power times cosine of theta V minus theta I. Right, again, and as I did it before, I just replaced theta V minus theta I to be equal to theta to make it shorter. And from this equation, I can then solve for apparent power. Right? So now another equation for apparent power from this equation would be that apparent power is equal to average power divided by cosine of theta. Okay. So now I have also several equations for apparent power, right? I have this equation that I've already derived earlier, right? I have the RMS times IRMS, right? That's another equation for apparent power. If you use RMS, if you use peak, you have VM, IM, right? Okay. Any questions? Okay. If there's no question, then let's move on to this example right here. I made several mistakes here, so please correct these in your book. We'll see that later. We'll see those later. But let's say that I have a component, a device right here. I use a box here for the device, and the voltage across the device is Vm at theta V. That's across the entire device, and the current through the device is Im theta I. Notice that in the device I define it to be an impedance Z that consists of R and X, right? It's a plus JX. So therefore, I know that inside this box, we have resistor in series with inductor, right? So that's how you get R from resistor. That's how you get JX from an inductor, right? So again, the voltage across both devices, both components would be Vm at theta V, and current through both would be Im at theta I. Right. Now the question is, how do you calculate apparent power? On Monday, we have the same example except for complex power. Let me scroll up to show you. Right there. See, this is the same example, except this one we use this example to calculate or derive equations for complex power, right? So I use the same setup, the same settings for the device, except now I'm trying to derive the equations for apparent power, right? And the first typo I have is this. This should be like this, right? Well, because it is apparent power. And then the equation right here is I squared times Z. So I squared times Z is equal to V squared divided by Z, right? Now, there is a mistake here because I give you Vm and Im, but what is I and V, right? So I should be more specific. This should be Im and Vm. But if I do that, then I'm missing the 1/2. 1/2 there, 1/2 there. So I'm going to rewrite it here, okay? I'm going to rewrite it right here. So the equation for apparent power for this example should be 1/2 Im squared times the magnitude of Z. For Im, I don't need the magnitude, right? Because Im is already peak. So it's always positive, right? So that's the correct way of expressing apparent power using Im and Z. Peak value of the current and the magnitude of the impedance. If you like to use voltage, which is voltage across both, you could. Then that's going to be 1/2 Vm square over the magnitude of Z. Right. Any question on that one? So please fix that these mistakes.
How do you know that JX is an inductor? Couldn't it be a capacitor?
I know it's inductor because it's plus
Okay.
JX, right? Yeah. Any other questions? If it's capacitor, then it will be R minus JX. Right. Just a reminder here that when you have L, that would give you plus JX, right? If it's C, it will give you minus JX. Right. Any questions? Maybe another reminder. How do we get minus from capacitance? What is X called, by the way? X is called reactance, right? Reactance. So you have resistance and you have reactance, right? For L, the reactance would be J omega L, right? For C, the reactance would be 1 over J omega C. Well, 1 over J omega C is the same as minus J 1 over omega C, right? That's how you get the minus sign for C. Hopefully that answers your question.
Yeah, thank you.
Okay. Now, going back to apparent power, I can also derive more equations for this example. And again, I have apologize, I have more mistakes here. I hope this is the last one. I believe this is the last one. We'll see. For this one, right, I'm using both voltage and current. Right, the previous setup, the previous equation right here, I'm using either current or voltage, right? Either current or voltage. But here I'm using both voltage and current. If that's the case, then it is Vrms times Irms. But I did a mistake here, as you can tell, right? I'm using peak values, and what am I missing from this equation?
One half.
The 1/2, yes. So I forgot the 1/2 for that one. So please fix that. So anytime you use peak values, there is 1/2 in the equations. If you use RMS, then the 1/2 disappears, right? Okay. We already got this, right? That's what we just talked about. Right? That's actually corrections to this first equation right there. We have it right here. And then you can also break down the power into two, right? Because we have two components. We have R and L, right? So let me redraw it here so it will be clear. We have R and we have L, right? There's a current right there, right? I, and then there's a voltage across both, right? But then if you want to break it down into two, remember that another equation for apparent power is square root of P squared plus Q squared, right? That we talked about earlier. Now that means I could break down the power here of the circuit into two powers, P and Q. Can you tell me where the P comes from? Where is the average power comes from out of these two? Where does it come from?
Resistor.
Resistor. Why not from L? Why is it that P comes from R only? Why not from L?
Because it's imaginary power.
Because, yeah, exactly. Because P of L is equal to, what is it? What is the average power of inductor? You must know this. 0, yes. And then that's why the only P that you get from, the only average power you get from the circuit, simple circuit, is from R, right? And by the same token, if you look at Q, right, we learned that Q of R is equal to 0, right? 0 of R. So therefore, the only Q must be coming from only L. And so this Q right here comes from L. And because of that, you got to be careful when you break it down into two, like this, right? Then if you want to use voltage, like this equation right here, using voltage, right there, you have to use the individual voltage, right? Individual voltages, right? One from, if you're looking for the P, that's the P right there. You can see that the voltage that I use is voltage across R. So specifically voltage across R right there, right? So VR square over R. See that VR square over R. And this is maximum, so that's why it's 1/2 at the front of the equation, right? And if you like to get the Q part right here, right? That's Q. Then you have to get voltage across the inductor. That's VQ or VX. I call it VX, sorry, right there. VX over X, right? So don't put L. Don't put VX over L. It's VX over X. Remember the unit for L is all is henries, right? So here you have ohms, then you also need ohms for this, right? So you have to convert L to ohms. How? Is omega L, right? That's equal to X, right? So be careful again, if you are using voltage, then use individual voltages to find P and Q. If you use RMS, then the 1/2 disappears, right? But same thing, you have VR over R, VR square over R, VX square over X, right? Any questions on this? What if you use current? So for both, right, current is the same, right, for both, because they're in series. So for current, you can find P, but it's going to be I squared times R, or the Q is going to be I squared times X, but it's the same current. So that's what I have right here. Right. Notice that it's the same current. I am, that's peak value, right? 1/2 is in the front of the equations. And if you use RMS, then the 1/2 disappears again. But notice that this is the P, this must be the P part, right? Because it's R, and this must be the Q part. Why? Because that's X right there. Right. Any questions? If not, then the next section talks about one of the powerful tools for AC power calculations. Is called power triangle, right? Realizing that we have complex power. Complex power is equal to P plus JQ, right? And this is just a complex number, right? Then I could represent complex power in any of the 4 quadrants, right? That's the 0, right? If I represent the x-axis for P and the y-axis for Q, right? That's the j omega axis, right? Then I could have complex power in any one of these 4 quadrants, right? For example, if let's say I have the triangle in the first quadrant, let's say I have the power equals to P1, and I have the Q equals to Q1 right there. Then we have the following triangle to represent this complex power. Right? That's the triangle right here, right there. Right. So that's the triangle that represents positive P and positive Q. Right. So for this triangle represents complex power S1. That's equal to P1 plus JQ1. Okay, here's the triangle. Now, so that means I know that this side right here, the height of the triangle must be our Q1. That's positive, right? That's positive Q1. And I know that the side right here, the base of the triangle must be P1 is also positive, right? So positive P1 means absorbing power, absorbing average power, and Q is absorbing reactive power. And if that's the case, then can you tell me what this hypotenuse represent? What is hypotenuse representing? What type of power?
Apparent.
Anybody? Apparent, yes, very good. We just learned about apparent power, which is the magnitude of the complex power, right? Which is equal to square root of P square plus Q square. Isn't that the same as the hypotenuse of this triangle, right? Right there. Oh, that's equal to F1 to be consistent there. So now at least from this power triangle, I get 4 different type of AC powers, right? I can get P1 from the power triangle. I can get Q1. I can get F1 apparent power. And from here, I can also get complex power, which is this right here, P1 plus JQ1. Right? And there's actually one more you can get from power triangle, which we have not covered yet. It's called power factor, right? And the angle of this triangle, that's the angle right there. That angle is called power factor angle. And that angle gives us power factor, which we're going to learn next, right? So you can see why this is powerful, right? Because once you know how to work with power triangle, then given any 2 parameters of the power triangle, you can get the other 3. You can get power. Let's say, again, if you have, so the 5 parameters that you can get from power triangle would be average power, reactive power, apparent power, complex power, and power factor, right? If you know any of these 2, any 2 of these 5, then you can solve the other 3, right? If you know Q and PF, then you can get the other 3, right? By using the triangle. Any question on this? Can I get a different triangle? Of course, you still have 3 different quadrants, 3 other different quadrants, right? If my triangle is right here, oh, you know what? Let's go back to this. So notice that this triangle is in quadrant 1, right? So that's this triangle. That's quadrant number 1. Can I have the triangle in different quadrant? Yes, for example, this one right there. That's in quadrant number 4. Right? It's the same positive P, right? But then the Q is negative, right? And we learned from one of the previous sections that if you have positive Q, that means this power triangle comes from inductive load, right? Because we know that L gives us positive Q, right? And the other triangle right here, you can see that Q is minus, right? The reactive power is negative, right there. It's quadrant number 4. So since the Q is negative, we know this is coming from C, from capacitor. So that's why it is coming from capacitive load. So inductive load will give you a power triangle on quadrant 1. Sorry, what did I say? Inductive or capacitive? Inductive load, right? Inductive load gives you power triangle in quadrant 1, whereas capacitive load gives you power triangle in quadrant number 4. Any question on this? We'll go through some examples, right? Making use of power triangle. You'll see how powerful it is, right? Any questions? If not, then let's move on to the next one. That's the last concept I want to talk about today. Power factor, right? So we've learned that 5 different types of power AC power, instantaneous, average power, reactive, complex power, and apparent power, right? And unfortunately, this is not the end of AC power, right? You still have one more type of quantity of AC power that is very important. That's called power factor, right? This is very commonly used in AC systems. This is to actually to signifies or identifies whether or not you have a good AC system by looking at power factor. One way to determine whether or not you have a good AC power system is by looking at the power factor of the AC system. The symbol for power factor is PF, and it is unitless, no units. How is it defined? So power factor is defined to be the ratio of average power to apparent power, right here. Right there. And we know that apparent power is equal to the product of voltage and current RMS value wise, right? So therefore, the same equation is equal to P over VRMS times IRMS, right there. So that's the general equation for power factor. And I have to make a note on this, that this equation applies to all types of AC waveforms. So it doesn't matter if the AC waveform is a sine wave or triangular wave or square wave, whatever AC waveform you have, then this equation applies for power factor, right? P over S, or P divided by VRMS over P divided by VRMS times IRMS, right? Now, for this class, right, we strictly will be using sine wave for AC power calculations, not for RMS calculation, but for AC power calculation. For this, for this type of power, we're going to use sine wave. Then there is a special case, I should say, special case equation for sine wave, right? That equation is right here. I'm going to derive it. Again, power factor is equal to P over S, right? And we know that the equation for P is equal to VRMS times IRMS times cosine of theta V minus theta I, right? And we learned earlier that V times I is none other than our apparent power, right? Now notice that from this equation right here, I could get the ratio of P over S, right? The ratio of P over S. I move S to the left-hand side of the equation, I get P over S. And look at what happened there. I get the ratio of P over S equals to cosine of theta V minus theta I, or in short, just cosine of theta. Right. So this is special case for sine wave, right? This is for sine wave only. So for sine wave, cosine wave, the equation for power factor is equal to cosine of theta V minus theta I, or cosine of theta. So I have basically two equations right now for power factor. One on the left applies to all types of AC power. The one on the right here, right, that only applies to sine waves. Any question on this? No. Now, since it is a ratio of the average power and apparent power, therefore the value should be less than 1, right? That should be apparent from the fact that if you look at the triangle, right, S is the hypotenuse, right? Oh, where do I have it? I have it up here as well, right there. Right. So S is right here, S the hypotenuse, P is the x-axis. So you can see that the ratio of P over S, maximum Y is going to be just 1, right? So it should be, the ratio should be less than 1, right? The maximum value you can get is equal to 1. When P is equal to S, then you have the result to be equal to 1, right? Okay, so therefore, since again, power factor is the ratio of P over S, therefore, the value of power factor should be between 0 and 1. Any question on this? Now, this angle right here, theta V minus theta I mentioned that earlier in the power factor triangle, right? That's the same angle as this angle right here. See that? Theta V minus theta I. And that angle is equal, is what we call power factor angle. Right there. So theta V minus theta I is power factor angle. Oh, there's the power triangle again. Okay. Now, that power factor angle right there. Yeah, if you are given the other two parameters, you should be able to get a power factor angle, right? For example, here, if you know Q, and you know P in the power triangle, then you should be able to get theta, right? Because we know that tangent of, let's call this theta, right? Tangent of theta from the power triangle is equal to Q over P, right? So therefore, theta is equal to the tangent of Q over P, right? So therefore, power factor should be equal to cosine of arctangent of Q over P. Right? This is just an example to show you that if you know two parameters in the power triangle, such as Q and P, then you should be able to get the power factor angle. And from the power factor angle, you can get power factor. Right. Any questions so far? All right. If not, then let's move to this other page again. Let's say I have a pure resistor load like this, voltage, current, right? And I have pure inductive load, pure inductor, V and I. And I have pure capacitor. Okay. Now, can you tell me what is the power factor of this first equation, power factor 1? Can somebody answer? Knowing
Would it
that
be
power
1?
factor. Oh, very good. Why is it 1?
Because they're in phase with each other.
Very
The
good.
angles are.
Very good. So it's going to be cosine of 0-degree angle, right? That's equal to 1. So you can see that if you have a purely resistive load, basically just a resistor as the load, then power factor becomes unity. This is what we call unity power factor, which is the ideal power factor. I'll explain it on Friday, right? Why is it called ideal? Why is unity is ideal power factor? And then what about, so very good. So if you have purely resistive load, then power factor is equal to 1. What if you have purely inductive or pure inductor load? What is power factor equal to? Anybody?
Wouldn't it be 0?
Okay, why?
Because the difference is 90 degrees.
Okay. What is the difference? Is it plus 90 or minus 90?
Plus 90.
Oh, very good. Plus 90 degrees. And how do you know it's plus 90 degrees, minus 90 degrees? Remember
Eli,
Eli.
yeah.
Yes, very good. Eli asked me. So for L, you can see that current lags voltage by 90 degrees. That's why theta V minus theta I must be plus 90 degrees, right? So that's going to be 0. Very good. Last one. If you have capacitor, what is the power factor there? Anybody?
Luis in chat also said 0.
Okay, very good. Why?
Because it would be -90, cosine -90.
Very good. Yes. See, now you know that if you have these three cases, right? Purely resistive load, that's going to be unity power factor equals to 1. If you have a purely inductive load, right, only L, nothing else, then power factor is equal to 0. And if you have a purely capacitive, just one capacitor, nothing else, then you have power factor equals to 0 as well, right? So these are the extremes, right? Remember, power factor goes from 0 to 1, right? But what if I have this case, right? I have R and I have L, and I have R and I have C, right? Same thing. I have the current there, the voltage there, right? R, L, V, I, R, C. Okay. Can you guess, right? The value of the power factor, right? Not a number, but just a guess. Is it going to be 0 or 1 or anything in between? What do you think for the first one? Is it going to be 0? Let me ask you that. Is that going to be 0? Yes or no?
No.
No, right? It's not going to be 0. Why not? Because it's not purely inductive. There's a resistor there. But that's why it's not going to be 0. It cannot be 0. Can it be 1?
No.
No, exactly, right? Why not? Because there's inductor there. It's not purely resistive. It's not purely inductive. So therefore, I know for this circuit on the left, power factor must be between 0 and 1, right? By the same token, I can also say the same thing for the right circuit right there, right? The power factor for number 2 right there, circuit number 2 is, it's not going to be equal to 0 because of there is R right there, right? And then it cannot be 1 as well because there is C in there, right? So again, for the right circuit, the power factor, if I have to guess, and it will be true, that power factor 2 must be between 0 and 1, right? You all agree with this? Right. Now, if that is the case, then how do you distinguish between load that is inductive on the left, that's called inductive, right? Why is it called inductive? Because it has R and L. And why is it called capacitive on the right side? Well, because there's R and C, right? So how do you distinguish between the two power factors? Because both of them is going to be positive value, but it's going to be between 0 and 1. But if I said, okay, the power factor is equal to 0.5. Well, what is that 0.5 coming from? All you see is just a number, right? 0.5. How can you tell that this 0.5 comes from inductive or capacitive? That's why we need more label for this power factor, right? So just saying 0.5 is not enough, right? We have to add something else. Now, the labels that we use depends on the current, right? If the current is lagging, what is it? Right here. If the current is lagging, such as inductive, then we call it lagging power factor. If the current leads, then it's called leading power factor, right? So if I go back to the previous circuit right here, right? On the left, we know current is lagging, right? Because it's inductive, Eli de-Eisman. Current lags the voltage. So therefore, power factor that is associated with the left circuit is called lagging power factor. So this will be lagging power factor. Whereas on the right, Eli de-Eisman, right? Current leads the voltage, right? Current here leads this voltage. So therefore, the power factor for the right circuit would be leading power factor. Okay. Any question on this? So now when you use power factor, make sure that you specify as well whether or not this is going to be 0.5 leading or lagging, right? If it's lagging, then I know that the load will be inductive, right? Any questions? what if I have this case? Yeah. What is the power factor of this? Is it going to be 0? Is it going to be 1? Is it going to be between 0 and 1? Right. Well, is it going to be lagging or leading? Right. See, these are different different questions that you have to be able to answer, right? Lagging or leading, right? How about this one first? The power factor, the value you can always calculate, right? But what about lagging or leading? How can you tell if it is lagging or leading? What do you do? What do you look at in order to determine whether or not it's lagging or leading?
Would it be direction of current?
Yes, so it would be from the phase angle of the current, right? With respect
okay.
to the phase angle of the voltage, right?
Hmm.
So this current will have some angle theta I, that voltage has angle theta V. So you look at the angles, right? Which one is lagging? Right? So you look at the current basically. Is the current lagging the voltage or the current is leading the voltage? If the current is lagging the voltage, that means we have a lagging power factor. If the current is leading, that means we have leading power factor. So always look at the current with respect to the voltage in order to determine whether or not you have lagging or leading. Is that clear? So in order to determine this, look at theta I with respect to theta V, right? Any questions? So again, as I said earlier, unity power factor is the desirable power factor. That's an ideal power factor. It would be hard to actually get unity power factor, right? I mean, think about it. In your house, right? It's not going to be purely resistive, right? The load in your house is not going to be just resistor, right? It's going to be, I would say, it's going to be more inductive. Why? Why is your house is mostly like this? Anybody? Mostly is inductive instead of just purely resistive. Can you think of any loads that would create inductive components in your house? That's a critical question, by the way. What is it? Anybody? Do you have any fridge in your house? Refrigerator? Right? What does a refrigerator have inside it?
Freezer.
Compressors, yes. Right? Or motors, basically, right? Motors. What's inside a motor?
Coils.
Coils, yes, exactly, coils, right? If you have air conditioning, same way, right? You have motors inside, that's also coils, right? Heater, same way, right? So those are big, right? Big motors. And that's why it's very common that our house is actually inductive. It's not resistive, it's not capacitive, it's mostly inductive, right? Okay. And I think, oh, sorry, one more thing before we adjourn. Another definition of power factor is by looking at impedance like this, right? If you have impedance, there's voltage across the impedance, there's current through it, and power factor again is by Ohm's law, the impedance is equal to V over I, right? And voltage has the phase angle, current has the phase angle. But if you do the Ohm's law right here, look at what happens with the angles. You get Vm over Im, and then theta V minus theta I. That's the angle again, right? So another definition of power factor is also equal to the cosine of load impedance, right? Cosine of the load impedance. Okay. And with that, that would conclude the session for today.